This is our CAD CAM software. We're using Gibbs CAM because a lot of big companies like Boeing and Big Auto and different companies use it for molds and pretty advanced works. It's perfectly adequate to do a knife. We got our start with pistol grips and actually been doing a bunch of behind the scenes stuff for the knife industry for about a decade. So this is our first design and we wanted to do something that was unique. So we had a little bit different angle than what most people put on there for the sharpening choil. Makes it a little harder to grind, but gives it a really cool look. We wanted to do a fuller with some holes. The holes are actually functional for braiding paracord, give it a kind of a unique look. Um, Fully chamfered around the outside, raised thumb ramp, got a pretty deep finger choil, and a pretty short grip where we're not wasting a bunch of space on the front of it. Kind of gets rid of the need for extra finger choil. The 3D modeling, we're not going to get too much into, but if everything's 3D modeled correctly, the fit and finish of the knife will just come out automatic. The CNC mills are holding about a human hair for tolerance. So if we have everything designed correctly, it'll come out correctly. This blade is going to be 187 AEBL. We like AEBL because it's super tough, it's stainless, it's machinable, and it's probably the best bang for your buck out of any metal that you can get. Um, we have a skeleton on the inside. And that gets the balance done correctly for the knife. The software will actually calculate the center of gravity. And it's right there about where that front bolt hole's at, just perfectly balanced. Spin that around. I like the hidden lanyards. You could run a lanyard tube through the backside and not interfere with your grip. If I turn the lines on, we have our Kydex modeled. Um, Again, I'm not going to get too much into the Kydex, but it's important that it's CNC modeled so we can make a precise Kydex fit for a precision milled blade. Turn the geometry on, it'll show you that we have standard spacing for your belt clips and your tech locks at both 3/4 of an inch and inch and a half. We'll go downstairs and take a look at that in a minute, and also pull in my 5-inch version. The 6-inch versions will be ready in about 3 weeks. 5-inch versions, maybe 3 months. On the 5-inch version, we wanted to stylize it in a similar manner, but also cut down on the grip length. When you put those in your hands, there's actually a noticeable difference between a 5-inch blade and a 6-inch blade. It's fairly uncommon for other makers. Most makers are having scale interchangeability, but we wanted to do something special on the 5-inch blade. We'll go downstairs and take a look at that in a second. I'll show you guys how we do some of the product development. This is 3D print software. This version's free. It's Orca Slicer. And it'll basically take our CAD model that we created in the other video, turn it into a plastic 3D part. 10 years ago, this print would have taken about 6 hours, and it might not have even completed because the 3D printers back then weren't that good. So this technology has gotten a lot better over the years, and compared to 10 years ago, I'd say the print times are about 4 times faster. The printers are about 10 times cheaper, and the filament prices came way down as well. So in this one, we will slice the plate, and the software will just kick out G code. I can rewind it, and it'll show you how it prints it. It'll do that base layer, and then it'll start building, tapers, the fuller. We'll get into the grips, start building the grips. In about an hour and 23 minutes, it's going to be done. It looks like we're using about 46 grams of filament. Filament cost is less than $1 in this case. So for the price of $1, I can't even make a crude prototype on a belt sander, throw anything in a CNC mill or a water jet. But once we get something we really like, we'll throw it on some more advanced machines to make better prototypes. We're using the Orca Slice again on an Ender 3V Plus. It's roughly like a $300 or $400 printer, and it actually kicks out good enough prototypes that we can evaluate our 3D drawings. So we got the MS6 loaded in the 3D printer. We can see a little preview down there. It says it's going to take about an hour and a half to print. So I'm just going to hit print, and then it'll go through a warm-up cycle and home out the machine, and then in a few minutes it'll start printing. We'll get some video of that in a second.
A few moments later.
So we got our steel loaded in the water jets, and here's the preview. That's pretty fast. We can slow that down a little bit. So to start in that corner, go up to the holes or perhaps the skeleton. Just work its way down. This cut's going to take about 4 minutes in person. The rendering, maybe 30 seconds, or if we speed up the rendering, it's instant. There the pumps kicked on. There's your pierce skeleton. Pierce on the lanyard. The nice thing about water jet is there's no heat affected zone to affect your heat treat on the steel. You're not introducing any extra stress. I'm going to lower the water and we'll be able to see it